Hi there and welcome back to my channel. In this video I would like to explain you my final project for data science course. You can add this project to your portfolio and you can use this project for your own final project in case you are also studying data science. So let's get started. First, I import all the libraries that I'm gonna use. So I need pandas for data manipulation, Seaborn for data visualization, matplotlib as well to building some plots, OLS and linear regression. These are two models that I'm using and I'm comparing them. To analyze my models, I use ANOVA LM, R2-square, and mean squared error. So let's get started. The most important thing is your dataset. Choose carefully the dataset that you're going to use for your final project. I recommend not to use trivial datasets because most of the time you're not going to learn anything. So make sure your dataset is decent, includes decent amount of rows, and the best would be that this dataset is from real world. In my case, I downloaded my dataset from redfin.com. So I'm going to show you how I use that. If you probably know, Redfin does not allow you to download more than 350 rows in one file, but I'm going to show you how I did it, and eventually I got like around 4,000 rows. So if I go to Redfin and let's choose homes for sale, my project is built on Miami dataset, and what I did was I was just inserting the zip codes. So for example, I know that 33132 is a zip code for downtown Miami. And I would go to table, and here in the bottom you have a button, download all. So you click the button, download all, and in your file you would have like 350 rows. Then I look for another zip code that is also in Miami, for example, not far away from downtown. Instead of 33132, I would write 127, and I know that this is for Edgewater, which is like next to Miami downtown. You can research online. You can go to ChatGPT and ask all zip codes of Miami or another city. Maybe you would like to focus on dataset from New York City. And I collected like 20 different CSV files, including 350 rows. All of them from Miami area, like Miami Edgewater, Brickell, downtown. And here is my example. So here I have 20 CSV files, and then I concatenated them all into one main Miami houses CSV file. So this is the code how I did it. If you're using my code, make sure that you rename your CSV files accordingly. So I start the name with the zip code, like here, and then just for me to understand and to remember, I just put also the name of the district, but you don't have to, of course, because the most important thing here in the code that your file starts with a zip code, starts with a number. Then you iterate through all files in your folder that start with a number. You want to skip the first row because it's a header, so you basically do the union. If you're familiar with SQL, you have a function that concatenates all tables into one with one keyword union, and then you append. I checked if I have duplicates, and in fact, in my case, my duplicates were the first row after the header. For example, all these files have the first row, which is completely empty except of this sentence. My code reads all these rows, like one row per each file, as duplicates. So in this case, they were deleted. You could also delete them manually because you don't need the empty row in your dataset. And of course, you want to create your own main file. I call that Miami housing dataset. You can call that whatever you like, but you want all your data in one CSV file. And here you have everything printed, exactly what you did, how many duplicates you deleted, and the last function I implement here is head. Head means that you print out first 5 rows of your dataset. As you notice, this dataset is not clean. The columns are not appropriate. We don't want any URLs to be a name of the column. We don't want these spaces in the name of the column. So and we also don't want all of these letters to be capitalized. So what I did later, I will show you, I modified slightly all these columns. But first, in each machine learning project, you would like to explore your data in order to clean it later to adapt to your models. So first, what you want to do in exploration step is to see which columns are empty, which columns are null, and which data type they have. For linear regression, you want only numerical columns. So I already see that we have like one column that is completely empty. So we don't need this column. We will delete it later. Some columns are not even appropriate for our analysis. For example, interested and favorite. These columns are metadata. It comes from the website. It does not predict the price. It does not even influence the price. Sale type. Even though all 4,501 rows are not empty, still, if you look at the data and it's here, this is just a metadata. It doesn't say anything about the house. So of course we don't need it. Then you want to check the statistics of your data set. The statistics is applied only to numerical data. This is helpful in every single project. Then I want to count how many rows I have in each column that are null, that are empty basically. So these two, for example, most of the data set is empty. And this is just the date for open house. It doesn't say anything about the price, right? And it's also empty. So I think we can omit it and drop these two columns as well. So next step, we proceed with the data preparation. Here we delete the columns that we do not need. We delete the rows that we think are outliers. So what is the outlier? I will show you later. But the main objective of this step is to get rid of data that does not influence the price, that can actually, if we do not delete it, can actually destroy our model. So here is the data. So address, city, and state of province. So here it will always be Florida. For prediction, we do not need these three columns as well. We have longitude, latitude, which is also the location. But address, city, and state of province are not even numerical columns. And that's why our linear model will not even accept those columns. Zip code, we are also not interested in that for this project. Price is the most important feature here. It's a response variable. It's our Y variable. We are looking for price. We are predicting the price. Beds and baths is also very, very important. Location here for this model, it's not appropriate. Square feet, we want to keep. Lot size is empty. We don't need this column in our model. Year build, we will keep it. Days on market, we will keep it for now. Price per square feet. We will drop this column because price per square feet is nothing else as price divided by square feet column. So this is like duplication. This leads to multicollinearity that we will mention later. HOA per month we will keep. Status, active, we don't need it. It's just metadata. These two columns we already said we're gonna drop. URL, we don't need it for the model, so we're gonna drop it. Source, MLS, does not really predict the price. And favorite, interested, we're gonna drop. We already mentioned it. Latitude and longitude, we keep it for now. We will see how it will work later. Now that we decided how many columns and which columns we are keeping and what we are dropping, we move to cleaning our headers. The best and easiest way would be to replace spaces with underscore and replace slashes with underscores. And all headers should be lowercase. If you notice here, we have one row where the price is empty. This one row we're gonna drop because it might influence our model. And of course we are not allowed to put a 0 instead of empty or null. The house is not gonna cost you $0. We're gonna drop that one row. But for HOA per month, those rows that are empty, we're gonna fill with 0 because Some houses, some type of properties might not have HOA. For the rest of the columns, beds, baths, square feet, year built, all empty rows we will fill with median. Now we move forward to the categorical variable. Property type should be encoded into 0 or 1 because, as we said, linear regression does not accept strings. It accepts only numbers. So the rows that have type condo will have 1 and other columns will have 0. The same as, for example, this house is single family residential. That's why you have 1 and all other columns are 0. So now we have to change our headers again. So we do the same operations. We replace slashes with underscores, minus with underscores, and we want to remove the parentheses. So now we have clean data, clean headers, only numerical data, which is ready for further analysis. And now we're gonna visualize the data to see if we have some outliers. So here we build different plots between price, because it's our response variable, versus all other predictors. And actually in this data set we have a lot of outliers. For example, this dot is an outlier. These dots are outliers. Here it's an outlier. How do you know it? Look at the x-axis. This dot indicates that your square feet is more than 1 million, which is huge. It's impossible that a house has more than 1 million square feet. Here, how many bathrooms we have? We have more than 15,000 bathrooms. We print those outliers. For example, print large houses where the square feet is more than 100,000. And here you have a huge square feet number, only 1 bedroom, only 1 bathroom, and the price is 539,000. So of course we want to delete this. Then we look for items where the number of bathrooms is more than 5,000. And here you have, okay, square feet, 15,000 bathrooms for only 2-bedroom apartment. So this is definitely a mistake. We don't know the true number of bathrooms. So these are our outliers and we want to delete them. Here we have HOA per month more than 40,000. Probably here as well was just a mistake. So we just delete those rows. Okay, so our plots now look a bit different. Next step in this project, or in any project that you are working on in machine learning, is to check for relationship and multicollinearity. What is multicollinearity? It is a factor that indicates that your data or your features depend on each other. So we create a correlation matrix, and here we see all features and their relationship to other features. Let's have a look at relationships between price and its predictor variables. So here you have price, and all these are predictor variables. We have 0.64 between price and square feet, which means as square footage increases, the price strongly tends to increase. Let's look at the price and HOA per month. We have 28. It's a moderate positive correlation. Higher HOA fees are associated with more expensive properties. Now let's look at the beds. So we have 0.21, which indicates that higher prices correlate with bigger amount or larger amount of bedrooms. Now let's see at the negative correlation we have between price and latitude. It's a mild negative correlation and it suggests a geographic trend. So as you move north, latitude increases and prices tend to decrease slightly. This is very interesting feature, how to see the prices versus location. So if you're working on a different data set from a different city, write in the comments below which location in your data set tends to be more expensive or less expensive. If you look at the relationships between predictor features, like for example bedrooms and multi-family 2 to 4 unit, we have 0.51, which is a moderate positive correlation, and it suggests that the multi-family units tend to have a higher number of bedrooms. Square feet and bedrooms have 0.49, which indicates that properties with more bedrooms tend to have more square footage, which is obvious and logical, right? Here you have the explanation as well. And probably in your project you would also like to create some visualizations, so you can create a pair plot and also a heat map. Heat map is very user-friendly, I would say, because here you have a bar which indicates from negative correlation to positive correlation. Darker color, like here for example, indicates strong negative correlation. So this is the same correlation matrix that we just discussed here, but displayed in colors, which is very user-friendly. If you want to present your project, use the heat map. Now, very important feature, before you implement your linear regression model, check for variance inflation factor. Variance inflation factor helps you to identify multicollinearity. Remember, less multicollinear your variables are, is the better. So the standard coefficient is not more than 5. So if your VIF score is more than 5, you have to do something with your data. And this is the best example that I can show you with this data set, because a lot of these scores are extremely high, more than 5 for sure. So what we are going to do, we have a few options here. We try to break this multicollinearity by dropping a column, or we can add more data. In this project, we are not going to add any data, so the only option we have is to figure out which variable we're going to drop. Since I have a lot of typed variables which include only 0 or 1, so this is first factor why the data set is multicollinear. So I try to break this, and that's why I'm trying to drop one variable, one type variable. My scores are slightly better, but still, it's a huge number. This is a huge number. So actually, what I see is that the location and the year built are highly correlated in this data set. If the variables are highly correlated, you basically just have a repetition. So they are not useful for the model. Now we try, so I'm not really like dropping the column, I'm just trying. I just want to see the VIF score. So that's why I'm not really dropping it in the in my data set. So I create a new variable and then I check the VIF data scores. So now instead of dropping one of the type variables, I'm dropping latitude and longitude. And let's see how the scores are doing now. We have high scores in our type variables. All right, so let's delete 3 variables, latitude, longitude, and one of the type variables. The scores are better, but still 14 is a lot. So my next step would be trying to drop latitude, longitude, location, and the year built. And surprisingly, I have perfect VIF scores. So this is another tip for you when you are working with your data set. Try to find a way to improve your VIF scores. This is very, very crucial before you start implementing your linear regression models. Okay, so I really like this because none of the scores are more than 5, and I update my Miami houses variable so that I have all the variables except these 3. Now I'm ready to use and implement my OLS model. So here I define the predictor columns. Price is my response variable. So this is the variable that I'm looking for, that I am predicting. And this is very simple function. You just type OLS. Here you type this formula and you indicate which variable includes your data. And then you say fit. So you are training the model. Summary method shows you the summary of the model. What is the first thing you're looking at when you have this output? First, what I always look at is my R² coefficient. This is a coefficient of determination, which means that only 47.8% of my data is explained by the model. It's not great, but the dataset is real world dataset, and you will never have 100% R squared in your real world dataset. So this is very, very normal, but not perfect, of course. So for this, I would say that I would prefer to focus next time on the dataset that includes only one specific district, because as we see that prices in Miami are extremely different from district to district, and even inside one district, the prices for the houses that are close to the water are so high in comparison to other houses in the same district that the model is just confused. Linear regression model is not perfect for this, but it's a perfect example for you to understand this and to have real world examples in your portfolio. So here I also explain F-test and T-test. So what is the F-test? If you look at this variable, F statistics and the probability, so this looks quite good, which means that there is sufficient evidence to reject the null hypothesis. And the null hypothesis for F statistics is that there is no significant linear relationship between any of the predictor variables, like beds and price, or square feet and price. And if you have the probability p-value here close to 0, or 0 in my case, you can reject this hypothesis, which means at least one of predictors is linearly related to the response variable, which is to the price. T-statistics, T-test, we have here, it's the individual feature hypothesis, and the null hypothesis of T-test is that the size of the property is not significantly related to price. We can also reject this hypothesis because all of these p-value for their corresponding t are close to 0 or 0. So use F-test and T-test in your projects to either accept or reject your null hypothesis. Another key factors while analyzing your model is to look at the residuals. Residuals will tell you if your model assumptions are validated. So here we have the plot of residuals versus square feet and residuals versus fitted values. This is very famous plot, and unfortunately we have here heteroscedasticity. Heteroscedasticity can be shown by this fan that is displayed in the plot, which means that the model's prediction errors are small and consistent for less expensive properties. As the fitted values on the x-axis increase here, the vertical spread of the residuals becomes significantly larger. This shows that the model's prediction errors are much greater for more expensive properties. This also suggests that the model's error variance is not constant and that its predictive accuracy diminishes for higher priced properties. We do not want this feature to be present. We also have a QQ plot, which is also a not perfect indicator of normality. So I would say that the assumption of normality and the assumption of heteroscedasticity are violated, which is another factor to use more complex models for specifically this data set rather than linear regression model. So here you see a significant deviation from the regression line, which indicates that the residuals are not normally distributed. All right, so now let's try the linear regression model from Scikit-learn. We split the data into 20 versus 80%, where test data 20% and training data 80%. We fit the data and we predict on the testing data. To analyze this model, we use mean squared error, root mean squared error, and R squared value. So here our R squared value is just very tiny bit better than in OLS. So it explains 48.4%, and mean squared error measures the average squared difference between the estimated values and the actual values. So we always try to get lower MSE. In this case, our MSE is huge. So again, the data set that we have is not perfect, but represents real world example. This project is available on my GitHub account, so you can always use the code. You can experiment with your own data set. And thank you for watching, and write in the comment if it was helpful for you.